This video provides some examples on how to solve trig equations using some of the identities that we've previously learned. So we already know identities like the Pythagorean identities, cosine squared theta plus sine squared theta equals 1. Now we've got our double and half angle identities like sine of 2 theta is equal to 2 sine theta cosine theta. That's one of our double angle identities. We've got cosine of 2 theta is equal to cosine squared theta minus sine squared theta, or can also be written as 2 cosine squared theta minus 1, which can also be written as 1 minus 2 sine squared theta. So we've got Pythagorean identities, and there are, of course, the other two that involve tangent and cotangent, and then double angle, and we have half angle identities that we could refer to as well if we needed to. So in order to solve this first example, we're trying to figure out what x is, and we're looking for x values in between 0 and 2 pi. So there could be more than one solution to some of these. And so if I start off by adding 1 to both sides, I have 2 cosine x equals 1. And then divide both sides by 2. Cosine of x is equal to 1/2. So now we want to think about, on the unit circle, where are all the places where the x coordinate is 1/2. And so we learned that at 30 degrees, or pi over 6, the coordinates are root 3 over 2, comma 1/2, because of the 30, 60, 90 triangle that we get here. And so that means at 60 degrees, or pi over 3, these are reversed. And so that's exactly the one we're looking at. We're looking for when is the cosine value equal to 1/2. So that happens at pi over 3, which means it's also going to happen somewhere else on the unit circle where the x value is positive 1/2. And so that would be when we're down here in quadrant 4. This point would also be positive 1/2, but negative root 3 over 2. So these are our two solutions. So this angle you could think of as negative pi over 3, but that's not within the bounds that we're looking for. So we have to go the long way around, and so that would be 5 pi over 3. So the solutions to this are x equals pi over 3 and x equals 5 pi over 3. For this next example, it might be helpful if we replace the tangents with sine over cosine. So I'm going to write this as sine x over cosine x times sine squared x, and this side as 2 times sine x over cosine x. So that ends up with sine cubed x over cosine x minus 2 sine x over cosine x equals 0. And so then if we factor out, if we put both these fractions together, they have the same denominator. So we could say that that's sine cubed x minus 2 sine x over cosine x equals 0. And then factoring a sine out of the top, we'd be left with sine squared x minus 2 and so then a fraction is equal to 0 whenever its numerator is 0. And so if we take the numerator and set that equal to 0, that would be sine x could equal 0. That would make this part 0, which makes the entire numerator 0, or sine squared x minus 2 is equal to 0. And so solving this, we know that sine x is equal to 0 when we're on the unit circle. Sine x is equal to 0 here. and here. And so that gives us the solutions x equals 0 and x equals pi. In order for this second equation to be 0, that would be the same as saying sine squared of x is equal to 2, which means sine of x is equal to plus or minus square root of 2. That's actually impossible because we know from graphing sine is always in between 1 and -1, and square root of 2 is outside of that. That's about 1.41. So a sine function can never be equal to 1.41. So we don't have to worry about the second component equaling 0. This has no solutions. So the only two solutions we get are x equals 0 and x equals pi. And we just check and make sure that we don't want that to make the denominator 0, because that would make that undefined. Cosine of 0 is 1 and cosine of pi is -1. So we're all in the clear. Those two solutions are our only two solutions, and both of them work. So now we'll work through our last example. We have sine of x times cosine of x is equal to negative square root 2 over 4. And so that might remind you of our one of our double angle identities. We learned that sine of 2 theta is equal to 2 sine theta cosine theta. So this, we have cosine theta times sine theta, which looks like this. And so one thing I might want to do here is just multiply both sides of the equation by 2. And now this matches this. Matches this. So that's going to be the same as sine of 2x. And if we simplify the right side, we get negative root 2 over 2. And so we want to think of angles that have a sine of negative root 2 over 2. So that quantity should sound familiar, because whenever we are at pi over 4 or 45 degrees on the unit circle, our coordinates are root 2 over 2, root 2 over 2. Now we're looking for it to be negative. So that means sine needs to be negative, so that happens here and here. So that is 5 pi over 4. We have the coordinates negative root 2 over 2, negative root 2 over 2. And here we have, that would be 7 pi over 4. Our coordinates are positive root 2 over 2, negative root 2 over 2. So those are the two places where sine is negative root 2 over 2. So that means our angle needs to be 5 pi over 4 or 7 pi over 4. And by the angle, I mean this whole angle 2x. So that tells us that 2x has to equal 5 pi over 4, or 2x has to equal 7 pi over 4. So if you divide both sides by 2, you get x equals 5 pi over 8. And this one, divide both sides by 2, you get x equals 7 pi over 8. So using our double angle identity, we were able to get two solutions for that one. That's it for our examples today. Have a great day.